that your job is essentially to connect all of them together and pray that they're working correctly in production, because there's so much complexity there that you can never be entirely sure. And the end result is really, even though you're trying to build something that seems really simple on the surface, there's an incredible and overwhelming amount of complexity that goes on underneath. And the end result is really that, what sounds like we should be able to ship in a week takes usually several months. And there's such a disconnect there. So I started thinking about this problem, right? And to maybe put it in a bit slightly different way, like building a backend seems really simple. And, most backends is just variations on this theme that you see here. You have a front end, it's sending some data to a backend. You're interfacing with some APIs, both external and internal. You're interfacing with some databases and so on. And then you just kind of do this over and over again and variations on this theme for 15 years, and then you've built Spotify. That's, at the end of the day, it's not much more complicated than that. It's just a lot of it. But that sounds really simple, but there's a lot more to it, even for the simplest of application, right? So you're dealing with build and deployment systems, you're managing YAML files with Kubernetes, you're setting up databases and other infrastructure, you're handling secrets and API keys and passwords and database connection, strings, and doing service discovery and provisioning servers. It's like an endless amount of stuff. And all of this stuff is pretty much unrelated to your actual product. Like, we want to do the stuff on the left, but all the stuff on the right is actually what consumes most of our time. And that's a problem, because that's not at all about our product. And everybody who's building with the cloud are doing the same things on the right-hand side over and over again. Whereas where we want to spend our time is on the left. So the real problem here is that there is nobody that actually handles the stuff on the right for you. It's always you as a software engineer. And this is a problem. There's nobody really that can help you. And the end result is you have to do the work, right? And so when we started to think about infrastructure and how we can get away from spending so much time on it, there's this concept called infrastructure as code, which is really great. There are tools like Terraform, CloudFormation, Pulumi, and so on that provide a better way of managing infrastructure. And it seems really promising at first, right? Like you're writing code instead of clicking around in a UI somewhere. You can just write code, which you're probably comfortable with since you're building a backend application. And that's great. But the downside is really that now we have two different pieces of code that should match each other, right? Like how you're writing your backend should correspond with the infrastructure you need, but they're really developed separately. And over time, they tend to diverge. Or you're making some changes in the cloud UI, and you don't do it in the infrastructure as code repository. It also tends to be very production-centric, which means if you want a test environment, it usually doesn't really work the same way. If you want to move to another cloud, you have to do quite a lot of changes. And so it ends up being a bit less useful than we would like. But the core idea is pretty good, right? Like we want some way of having our tools manage infrastructure for us. And what I realized is what we really want is our tools to understand the architecture that we're building. So if you think about it, like when you build an architecture like this, like we are seeing on the screen, you have your front end, which is talking to 3 different backend services that each have their own database. You have some API calls between them. You have some events going between them. Most people could actually translate this into the appropriate infrastructure in the cloud, right? What's really needed is just this level of understanding. And from that, we can actually do a really good job of translating that into the appropriate infrastructure and deployment that we want in the cloud. So this is really what we want our tools to do. And the problem, of course, is that our tools really don't have this understanding, right? They're just treating it either as black boxes like Docker containers, or they are, just treating it as files and lines. There is no concept of like understanding how a system fits together. So I had a crazy idea, right? Like, what if we could teach our tools to understand what it is we're trying to do and arrive at this picture that we have in our heads? Then they could be much more helpful by, aiding us in our work to actually take the software we write and deploy it as a distributed system, manage the infrastructure for us, set everything up, and just be much more contextual and useful when we're working with that software. So that's what we've been building with Encore. I've been working on this for more than 3 years by now. And the core idea is really to build this understanding. And we're calling that the Encore application graph. And it's pretty much, going from code into this sort of graph. And I'm going to show you a bit more concretely what I mean by that. So I'm going to switch over and share my editor. So here we're looking at a picture of a really simple backend application, right? And what we can do is we're going to try to replicate some of the stuff we just saw. And I'm going to put this in a separate tab. So I'm going to use the syntax we have from Encore, where you define APIs by using this annotation and then creating just a regular function. And this is just going to be a placeholder to illustrate. But if you do this and you hit save, you can see that Encore understands that this is actually an API that we should expose. So it turns this into a dedicated microservice, this order service. And we're connecting a load balancer into it. So this is actually exposed as a public API. And let's create a separate microservice, which is the payment service. And we're going to call this pay. And we're going to make this a public API as well. And now you can see that it hooked this up as a public API connected to our load balancer. But now we don't actually want this to be public because this is a sensitive API. So we're going to make that private. It's no longer connected to our load balancer. We can go over to the order service and we can call this. And with Encore, the way you do API calls between services is just by importing the other package and then calling the function. So we can just treat it like a regular function call. And when you do this, it immediately updates to reflect that the order service is calling the payment service. And the final thing I want to show you is we can create a really simple database over here. And you do that by creating a migrations folder where you define the database migrations. And this is just a placeholder just to illustrate. And here you import the SQL database package from Encore. And we can just execute it, execute the query. Something like this. And when we hit save, Encore updates its understanding to see that, oh, this service needs a database. And when we then deploy this application, Encore will set up that database for us. So this hopefully illustrates what I mean by having our tools understand the systems that we're building. So how do we actually do that? If we go back over to here, the core idea is really to find a really compelling and easy way to develop distributed systems by providing a really natural way of expressing, concepts that we want to have when we build distributed systems. So on the coding side, that means, defining services and API endpoints, which I just showed you, doing request and response schemas for those APIs, making API calls between them, defining and using secrets and API keys, and so on. And on the infrastructure side, we want to make it easy to use databases and understand the database schema. We want to be able to use blob storage like Amazon S3 or GCS from Google. We want to have caches like Memcache or Redis. We want queues and PubSub and cron jobs and so on. So these are all the concepts that we're building our distributed systems out of. And we want to express them in the way I just showed you with a very natural way directly in our code that enables our tools to really understand what it is we're doing. And when they understand it, they can be much more helpful in working with us and simplifying our lives. And the way we're doing this, just to illustrate, is pretty much like a compiler, right? If you've used some of the Go AST packages and Go parser packages in the standard library, the way they work is you input some Go code, right? And it parses and analyzes and it builds up on an abstract syntax tree. And that consists of, it's a tree of a bunch of nodes. And those nodes are things like function literals and if statements and binary expressions and so on. And that is what the compiler then uses to translate it into machine code. And that's a really complicated process, but I'm skipping over that part. Encore does the same thing, but it creates what we call the Encore syntax tree, where the nodes in the graph are distributed systems concepts like services and databases, API endpoints, API calls, and so on. And our compilation step is to take that syntax tree and turn it into, provisioning infrastructure in the cloud. But it actually turns out that we can do a lot more with that. So we can also, generate a bunch of code to reduce boilerplate. We can generate API documentation that's always up to date. We can instrument your application for much easier debugging with distributed tracing and so on. So this is really the core idea behind Encore. And to maybe make it a bit more concrete, I'm going to do an actual live demo of the product. So now I'm going to share my whole screen. And hopefully you can see this. I'm going to, oops. Let's just do this. So the first thing we do is we create an application. And I'm going to use the Trello clone just to have something to play with. And let's open it up in Visual Studio. And when you're using Encore, the way you actually run the application is always just Encore run. And the first time it will take a few seconds. I guess I should do this. I was using a development release. There we go. And now it's up and running. Now it's pretty hard to understand what a backend is doing without looking at a front end. So we've actually built a front end just for demo purposes. So here we're going to choose the local development, and this is not connected to my computer. And since this is a Trello clone, you would expect that you can do Trello things. So we can create columns, we can create cards, we can drag them around, when we refresh, they're still there because we're storing all of this in a database. So if we go back here, you can see that this generated a bunch of API calls. And if we go back here and we take a look, the code is actually really, really simple. So this is the same concepts we looked at earlier. You know, to define an API, you just have this annotation. You have this function where you the input to this function ends up being the request parameters, and the return type from this function is the return response schema. And this is how Encore understands what your API is doing, and it can do a lot of cool stuff with that. So when you're building with Encore, you get this really easy to use developer dashboard that I just opened up, where you can go ahead and you can view all the documentation. You can see the inputs to all the APIs. You can see the response fields. You can even call it directly from here, and you can see what's going on inside. And if we'll go back here, you can see on the right-hand side, you get a list of all of the requests. So we can actually open them up and take a look. And this is what is Encore's distributed tracing view. And this just works out of the box. There's nothing you have to do to get it. You can see here that this request first did a database query. This is like a timeline. And once it completed, it spawned 2 different Goroutines. And those Goroutines made API calls to other services. So here was an API call to this endpoint. This is the request. This is the response. At the same time, we made an API call to this endpoint. You can open it up and see where in the code this is happening. And what's interesting is if we go down to this, this line 122, you can see that the way you do API calls is like I showed you before. It just looks like a function call. And that's really powerful because you get compile time auto completion on your APIs. So if you try to pass in a string when it expects on int64, the compiler will tell you and show you where the problem is. So this is super useful when you're making changes to APIs and you want to make sure that you updated all of the places where you're using that API. And finally, when you're happy with it, to actually deploy this to the cloud, all you have to do is type git push Encore, and that will trigger a build. There's a whole cloud platform that we built that actually takes this and orchestrates a deployment in the cloud. So this will build it for you. It will run the tests. Once the tests complete, it will provision the infrastructure, deploy the code, and then your application is up and running. And you can have multiple environments. You can even deploy it to different clouds, whether it's GCP, AWS, Azure. It all works the same way. And then you get metrics, you get logs, you get tracing, you get API documentation, and lots more that I don't even have time to show you. But hopefully you get a core, an understanding of the core idea. And with that, the real benefits of doing this, right, is there's almost no boilerplate. We can do some pretty crazy stuff with the Encore syntax tree that I just showed you. And finally, it works everywhere, right? There's no changes you have to do for local development versus production or a test environment. You just write code and Encore takes care of setting up the infrastructure for you. And maybe best of all, pretty much everything I've showed you today is open source, right? We've open sourced the parser, the command line, the compiler, all of the static analysis, the runtime, the tracing, you name it. And there's a lot to dig into here. I don't have time to go into it, but I guess I will go back here and Okay, it's still deploying. I was going to show you when it's finally done. So now it's just migrating the database, and then it will be up and running. But once that's done, it's all up in the cloud, and we can get on with our day of actually building software instead of managing infrastructure. So that's it for me. Thank you so much for listening. Happy to take questions.
Yeah, that was great, Andre. Does anybody have any questions? Feel free to take yourself off mute and ask away. Thanks for sharing. Anybody? If you want to drop it in the chat, I'll also take the time to read it. How long do you think it takes to deploy, Andre?
Oh, it's probably done already.
Okay.
It's usually faster than this.
Sure. Oh, wait, Bill, did you want to ask a question?
Yeah. So very impressive demo.
Thank you.
And I was wondering, when you deploy to GCP, how does that actually work in terms of the pricing? I mean, I guess you're just providing the infrastructure and it works on like Google Cloud Run, or how's it deployed?
Yeah, so we're like not at all trying to like make this about like, you know, all of that is owned by you, right? Like we're not trying to take control of your infrastructure. We're not trying to be some sort of middleman. Everything that happens on your cloud is yours. And so you connect to your own cloud account. Maybe I should have showed that, but essentially you give Encore permissions to manage a GCP project. And in that project, it will set up the necessary infrastructure for you, depending on what your application needs. So for a production environment, we set it up with GKE cluster, so Kubernetes, as well as for relational databases, that's managed Cloud SQL. We're working on more deployment options. So supporting Cloud Run, for example, with App Engine is also a possible deployment target. And then we'll do similar things for other cloud providers, like the corresponding things. But right now it's only Kubernetes that we deploy to for simplicity, since that's very standardized across the clouds. But we'll do more like cloud specific options over time.
In terms of the storage, it's Cloud SQL, not like Firestore or DynamoDB on the Amazon side.
Yeah, the only storage that we have like native support for right now is Postgres relational databases. So that means Cloud SQL on GCP. It means RDS on Amazon. It means like Postgres for Azure or whatever it's called on Azure. And over time, we'll add like more types of databases, both key value stores, NoSQL databases, more scalable things, whether it's big table or whatever. And those will probably be more cloud specific because there's less standardization across clouds there.
Thanks.
Okay, great. Any other questions? I know we just had one in the chat, which I think you just answered the question for, as related to which clouds you supported. Anybody else have any questions for Andre tonight?
I have a quick one here. I saw you have a fork of Go in the Encore Dev organization on GitHub, and I'm curious why do you maintain that fork? What does it do?
So it's not really a fork. We have like a super tiny patch on top of Go, which is really about adding instrumentation for the tracing. So when you're using tracing with Encore, it works for everything you do, and you don't have to do any instrumentation and so on. And we do that in the runtime for two reasons. One, it's much more performant since we can tie it to the Go routine directly. Secondly, we add that instrumentation when you're doing HTTP requests. So that is like a one-line patch to the HTTP client. So that's really all we're doing. There's nothing else to it. I think it's a single commit, or maybe it's 2 commits or something. So you can take a look at those, but they're very, very minor.
Okay, thank you.
And we're keeping it, it's rolling, so we're keeping it up to date with every point release of Go.
Oh, thanks, Andre. Any other questions tonight? We have time for one more. Going once? Going twice?
So there's one
Andre,
in the chat.
Yeah. What is the most complex example people have used Encore so far for?
That's a great question. We open sourced this about 2 months ago, and I think already 6 or 7 companies are building their products on top of it. And it's really all over the place what people are doing with it, which is really cool. We have one company is building like an e-commerce API for optimizing the boxes that you're shipping stuff in. And then another company is a Stockholm-based startup that are doing like a content recommendation platform for mental health. And then, I'm not sure I can talk about the others, so I don't want to speak and say something that I shouldn't do. But it's really like we're also having people build like DevOps projects. Some is more like conference related. It's really quite all over the place. But it's, some of them, the e-commerce one I mentioned, they've been building on top of Encore for more than a year now. So they're, 10 people, and it's pretty complicated, and they're running it in production, and they're super happy. So quite a bit all over the place, but generally, back-end distributed systems, scalable systems, that sort of thing.
Awesome. Andre, do you think if it just takes a couple moments, would you like to show us the result of what you put together?
Oh, yeah, sure. Yeah, so this is just, now it's up and running in the cloud. There's not much more to it. What I was going to show is, I guess what we can do is, so this was our showcase where I connected it to my local computer, but we can also connect it directly to the cloud. So I'm going to take my app ID here, and I'm going to put in prod. And now it's running against my production environment. So now there's no board here. We can create a new board. We can create this. We can move it. Oh. All right. And if I go back here, you can see that this just generated a bunch of traces. You can click on them. You get the same sort of experience for production. So there's very little that is different for local development versus production. We're making it work in a very seamless way. If we go back here, you can do things like, I want to connect to the database. For local development, it's just DB shell and then the name of the service. If you want to connect to the production database, it's just tell it like connect to the production database, and then you have a shell to the production database. So yeah, it's all very seamless. It should just work. You can curl it. So that's
awesome. Well, Andre, thank you so much for taking the time, and especially from coming to us all the way from Sweden. That's one of the benefits of this pandemic. And now, I don't know how many more online we'll have, but really, thank you for taking the time to share with us this evening. It really means a lot.
Yeah, my pleasure. I hope we don't have too many of these, for
Yes,
better
I
or
hear
for
you.
worse.
We would all love to get back into person for sure. Well, thank you very much. I'd like to take the time to introduce our next speaker this evening. Also, if you want to get into the JetBrains drawing for an IDE, please send me your email address and name in the chat as a private message, and I will add it for the drawing at the end. But at this time, I'd like to introduce to you our next speaker, Sudhindra Rao, currently working at JFrog, awesome company, by the way, as a development manager to help build communities and partnerships to provide visibility into JFrog's Liquid software mission. He's been working as a developer architect for critical business applications developing in multiple languages, including Go, Ruby, and Java. And after having worked with traditional application development, Sudhindra became part of the Pivotal team and built their Kubernetes platform offering. So without any further ado, I'd like to turn this over to Sudhindra, and thanks for joining us tonight.
Thank you, Ari. I hope you guys can hear me well. And I'm going to share my screen. Let me know if you see the presentation and not the meetup, which is on my other Google. You can see my presentation, right? Great, thank you. So treat this as an experience report, or just how things have been in my journey in learning Go, and then basically going to the next level on Go and learning in concurrency and applying it in real world. And I did a little bit of this at Pivotal, so I'll share that. This is a little bit about me. I have done a bunch of Ruby. I did non-computer engineering jobs before I switched to computer engineering. I joined Pivotal and was a GoLang skeptic. I came from the Ruby world and I found a lot of disconnects in how Go is built. And from there, I have come to this stage where I'm now talking to you all about my experience with Go and how much I learned about it. And currently I'm at JFrog, like Ari said, helping the partner engineering team. So when I was preparing this talk, sorry, this is just an insert about the slides and the video that will be posted. Like Ari said, make sure you ping him to get into the raffle, and Ari will do the rest. Also, don't forget to rate my talk after the talk is done. Yeah, so when I was thinking about concurrency, and I'm a little bit of a movie buff, this movie, Memento, came to my mind, and there was a lot of some similarities in how concurrent programs work and how this movie was played out on the screen. So I thought this was a good metaphor to explain how I built the concurrent system and how we were actually fighting the same demons. In this movie, if you haven't seen this movie, and I recommend it, it's a Christopher Nolan movie. In this, the lead is trying to chase and find out who caused him pain, and he's trying to avenge his wife's death, wife's murder, basically. The key thing about this movie was, like concurrent programs, things happen out of order, but in the end, things fall in place and the whole story unfolds. And that was sort of, that mystery was sort of intriguing to me, and I thought I could apply that to add a little bit more fun to a technical talk, to a technical topic. Oh, wait. Okay. So like I said, this talk will be sort of out of order, but things will sort of fall in place at the end. So I'm thanking you for being here. And the frog on the right sort of represents me right now, a little bit nervous about talking to you guys and trying to share my journey. Some references that you might find useful, and some things we will talk and touch upon during this talk. I'll obviously talk a little bit about Go programming language and some of the concepts around concurrency. There's a book and a website called Effective Go, which I used a lot. The GoLang playground was really useful. I'll refer to BOSH, which is a Cloud Foundry technique to manage virtual machines and manage resilient distributed systems. And obviously, I took a lot of inspiration from the movie. So you'll see some association of concepts in the movie. Also, we'll talk a little bit about Kubernetes, not a lot, just that we built a platform and the tool that we use to build that platform called Pivotal Concourse. Yeah, so like the movie starts, we'll start with the end, right? He finds the problem. So we found the problem. We had a build that was 6 hours long, and we reduced that to 2 hours by implementing concurrency in GoLang. We did not have error traceability. When the build failed, we used to just rerun or retry. We didn't know which part of the build failed and why. So we added that error traceability, and which meant that we had failures, but we could get fast feedback from those failures. And we also were able to trip the build as soon as the first failure occurred, so that we don't have to spend the rest of the time building it. And I know 6 hours to 2 hours doesn't add up to 400% improvement, but I'll explain that as we go along. That also showcased a developer day, a day in the life of a developer and how things work when you're building big, large systems. But you will be good to know. You will be glad to know that we actually were able to deliver something well. So the main characters in this talk were we are building a Kubernetes platform. What does this Kubernetes platform do? You can deploy it to any cloud, and we were at the time supporting I think 6 clouds, 6 different clouds like Azure, AWS, VMware, vSphere, private clouds, couple of private clouds, Google, of course. And the key thing that we were proud of was how the platform was built to help with day 2 operations. Meaning a platform being able to, you being able to install the platform is one thing, but you also being able to upgrade it from time to time without any maintenance was what we were very focused on. So we wanted to relieve that pressure of downloading and installing multiple things. Instead of that, we packaged this whole thing as a platform, and we used to release new versions as CVEs were discovered and security fixes were released. Right. So that's how we wanted to help the DevOps people. BOSH was a key player in building this platform. For people who haven't used BOSH, BOSH is like an Uber manager of your distributed system. You can manage VMs. It can monitor VMs. If VMs go down, it can bring up new VMs. It can manage scaling. It can also compile stuff on the fly, because when it wants to bring new VMs, if it gets a source that is not compiled for a particular OS, it can compile it. And it can maintain a cache of these things, because it needs to do these things fast, right? When you need to scale, you need to do, if you have cached binaries, it greatly improves how long it takes to bring up the platform. We will not touch upon the BOSH director part of it. We'll talk about the compilation aspect of it. But if you're curious, feel free to go to bosh.io and find out more. A very powerful technology. What this needed was a good, reliable, continuous delivery system. We insisted on automating everything, automating tests, automating builds, automating how the build progressed from one stage to another. So we had complex build pipelines built in Pivotal Concourse, which allowed us to chain things, right? And one of the things that we were proud of doing was we were helping our customers go from older versions to the newest version. So we supported N-1, N-2 versions, so that people had time to migrate from one version to the other. And we tested all those upgrade variations. So at the time that this system was being run in the beginning, there were at least about 49 acceptance environments, meaning variety of clouds, variety of networking options, variety of storage options being supported, right? And it becomes an n by m by p matrix when you try to support these. And each of them takes multiple hours to just come up with virtual machines, and then a complete Kubernetes platform comes on it. So it is a multiple hour exercise to test it on all of these, right? So automated everything was the key. So what happened? Every single day in the initial days, we found ourselves doing exactly the same thing as this guy. We woke up running. We did not know why we are running. We used to realize after halfway of our running that, oh, we are trying to rebuild this tile. Oh, this tile failed. What is the recourse? Probably run again, run faster, and try to get another tile. Every single failure was super expensive. And running through those 49 acceptance tests, acceptance environments used to take upwards of 72 hours, which is, if you think of 8 hours of a weekday, then that is more than a week's worth of work. And our default was to rerun because it was so hard to figure out what went wrong with a particular tile. The package thing was called a tile. The package Kubernetes platform was called a tile. Right, and we found ourselves running and sometimes wondering why we are doing this, right? Although given that we had all the right intentions, there were limited things we could do to improve, and we still had to deliver the platform at the end of the day because Kubernetes was being released at a certain cadence once every 3 months, so we had to keep doing that for our customers. So there were limited things that we could fix. What are the basic mechanics of building this tile? We had a list of dependencies. Think of them as binaries. One binary for your networking option, one binary for your storage option, one binary to connect these two pieces together, one binary that has modifications to your Kubernetes controller. All of those built against a target OS. And so when people handed us the list of dependencies, and this came from multiple teams which worked on these separate components, when they came to us in different forms. Sometimes they came to us in source form, sometimes they came to us in pre-compiled form, and sometimes they came to us in compiled form. Also, we leverage the BOSH cache because BOSH also, if it has compiled something before, it will retain that cache so that we can reuse it if it's the same version. And we also implemented our own cache, in a Google bucket, where we would store known successful builds. So that if somebody sends us the same thing that needs to be packaged with the newer tile, we'll just send it across, right? So our process was try to find it in these caches, if not compile it, and then send it to the combination where the whole installer is going to be built. Once this installer is built, then the 49 environments are triggered and the test begins. This creation of this installer used to take upwards of 6 hours because through this process. And at that time, we were compiling only for one single OS, which was, I think, one of the Linuxes. I forget, it probably was Ubuntu because that was the most popular one being asked. And we had some challenges doing that. And this was all okay for one OS and a handful of dependencies. But every so often, we were hit by one of these latencies. In this picture, every single cache or every single network or every single line had its own different latency, and we did not have the chance to optimize for that, right? So we found out that there is network latency to download something, and just to put things in perspective, these are all megabytes worth of packages, hundreds of megabytes. The eventual tile was about 4 gigabytes. Sometimes GCP would go down, and it would come back up in a while, and we had to deal with that latency. Compilation was the heaviest operation because it took upwards of 30 minutes to compile some big binaries. Sometimes the resource was busy and we had to wait on those resources. And of course, when we built for a new OS, we found that building on a new OS takes different amount of time. Building on one version versus the other, it's a different ballgame. And adding to this was the complexity of building for Windows. right? So this was basically our John G, and we needed to deal with him. What did we have in terms of tools? The guy in the movie has his camera and tattoos all over his body to give him clues of what who he should trust and who he should not. In our case, we had GoLang and tools that GoLang provided to improve on the latencies and to improve throughput from going from 6 hours to something shorter and faster. So if you haven't done much of concurrency in Go, I'll just walk through a couple of concepts and that we used. So Go has this concept of Goroutines. Goroutines are similar to threads, but they are much more lightweight, and you can have hundreds and thousands of those without causing serious concerns in terms of memory. And it uses its own scheduler instead of depending on kernel scheduler. So they are cheaper to schedule, reschedule, and all of that. And it limits how it manages local storage, and it starts with the smaller local storage, and that's also the power of Go. That's what I learned when I dig deeper. That's what I learned. That's what I thought was really powerful in GoLang. So we used Goroutines. So we'll come to that. Another concept that I learned along the way when we were trying to look at the old system that was in there was channels. And channels is such a powerful concept. A channel allows you to communicate between two Goroutines, and you can have a publisher and a listener, and the listener will block until there is a message to be read, right? And that itself is a good synchronization mechanism without having to worry about synchronization. So channels support like unbuffered and buffered, so you can have 10 messages waiting for a buffer channel versus one message waiting until that is cleared for next message to come, right? And there's a tenet that Effective Go promotes, like do not communicate by sharing memory, instead share memory by communicating, share memory by, and that's more powerful than having all these mutual exclusion concepts to tie down how memory is shared. More importantly, there was another concept that I learned when we were actually writing the new system to build and build this tile, is the concept of pipelines. What are pipelines? Pipelines actually allow you to use channels in a very creative way so that you can chain operations. And typically, you may find that your system is a chain of operations, and subsequent operations are waiting on the previous operations and all of that, right? And channels provides a very effective way of not having to manage synchronization between these steps, and that was really powerful. Unfortunately, the Go programming language book dedicates only about a page and a half, so you might need a mentor like I had to actually show you this concept and help you through it. But do look through that when you try it on the Go playground. You will learn a lot more about it. But I thought this was really powerful, and this is what we ended up using for building the new system. So initially when we started building the concurrent program, we had a scatter of wait groups and async wait groups and some differ calls and a mechanism to manage these threads. And what we found is they present the same problem that you have in other languages where threads are used. And then you have to be the bookkeeper of those threads, make sure synchronization happens, and actually, you don't end up in a deadlock situation. It was fairly easy for us to get into deadlock situations, even in our tests, where in some cases we were using mocks. Even in those cases, we ended up in deadlocks, right? And that is when we talked about pipelines and switched to that. So I'm not saying that you should never use these mechanisms, but these were not appropriate for the complexity that our system had and the kind of chain of events that we needed to depend on. And as as the character in this movie keeps on saying, don't forget the basics. Keep on looking for signs where things are confusing, and then go back to your basics. They'll always help you. So what helped us along the way in building the new system, and I'll come to it shortly, is focusing on test-driven development, making sure our code is manageable. We are breaking it down. Identifying responsibilities of the small pieces that form the whole system, and last but not least, encapsulation and trying to hide things. In our in the older system, we had a bunch of channels, but they were all scattered around, and you had to read multiple channels to figure out the state of the system, right? And we thought that was not efficient enough, and we had to infer instead of it being obvious what the state of the system is. So now let's look at what the new code is and how it looks and what ended up happening. So this was the basic algorithm, right? We were given a list of dependencies. We were asked to build for a new OS, which was the challenge. And we kept on asking these questions over and over for each of those dependencies. If it's a binary, then just download the binary and form the installer. Obviously, before you form the installer, you're waiting for all the binaries to be built. So there is a waiting for this. And if not, then go through the process of downloading sources, because you had to download sources from Git or GitHub or GitLab, wherever they are available, depending on whether they were open source or not. If they were precompiled, if they were precompiled, they're probably in the cloud cache. If they are not compiled, then compile. During compilation, also ask BOSH. If BOSH has it. If BOSH has it, then we are lucky, and we'll just push it to the cache on the cloud and then further install it. So there were a lot of opportunities for making things concurrent, and we leveraged that as much as we could. So just a little bit rundown on how the new code looked. So we had a bunch of channels. So we went from download, then compile, and then publish, right? So every single release or every single dependency, as we called it, went through this process of figuring out what needs to be downloaded. Sometimes it is source, sometimes it is the binary. Once it is downloaded, then it goes to the compile stage. If it is already compiled, then it skips and then comes to publish stage, right? And so this is how a pipeline would look to you. So going from one channel to the other, and the download worker uses the download channel as its input, and then it outputs to the compile channel, and so on. One of the key things when building this pipeline was figuring out what data needs to be together, what data needs to be encapsulated. And previously we had the release candidate, its binary path, and its source path, all of that as an object, and its result somewhere else. But then we figured out that there is no need to put these two things into separate places and then trying to figure out where all this data went. We actually created a combined object which had the binary details, the error state, the final result. So every time we were curious about what is the state of a binary, we would ask this release candidate, and that would have all the information that we needed. So figuring this out did take us some time, but I think when we figured this out, writing code became super fluid for us. So remember to go back to this was our learning. And while doing this, we discovered a number of objects that would help us break this complex system down. So we had like I said, the release candidate. We separated BOSH operations. We separated storage operations. We even went down and separated different kinds of storage operations, like interacting with GCS bucket, interacting with BOSH cache, figuring out how to update the result, and also created a number of, broke down the main process into a number of pieces so that they all could become the system instead of the old style of one program containing every single thing that the program needs to do. And figuring out the encapsulation, figuring out which objects are important in our system actually helped us figure out the termination condition, because we had a limited number of things to do. Even though our program is concurrent, we didn't want to end into a state where we are just waiting endlessly for things. We knew that we needed to compile, let's say, 25 dependencies. We knew that if there are 25 errors in the results box, then we are done. We compile all the 25 and we cannot build the tile. So figuring out the termination condition gave us the guarantee, and it also helped us test, like, how are we doing if we are going from one stage to the other. Now let's compare this to the old code. Why did we have to do this? What did we find that was not helping us go to the next level? So when we looked at the old code, this is how it was, right? There was a single Goroutine, which had a channel which went through releases, and it picked a release and tried to figure out. In this case, release meant the binary or the dependency. It picked a release and figured out what the state of that release is. And this seems simple. Okay, you have a Goroutine, and this is fairly concurrent, right? If you have 20 dependencies, there will be 20 Goroutines to process. But basically, when we look deeper, this is what happened inside, right? The process release function called the download function. The download function called the compile function, meaning if the download is not a compiled binary, then go and compile. And that called the publish function. And then that called, and every time we published, we also signed it with a SHA so that we can verify whether it was the correct binary. So there was a cascade of this. And there were a lot of opportunities for adding concurrency because downloading operations and compile operations have different latencies. So we were not leveraging that. And that added up to the 6 hours or 8 hours of build time, right? So having that separation helped quite a bit in actually leveraging everything that all the resources that we had at the time. Again, this termination condition was similar, although this looks even a little more clunky because we are trying to range through a set of results. We're trying to figure out if every single time we're trying to figure out if we have enough results, and then we are going back and stopping workers. We had none of that happening in the new code. And none of the anxiety of whether we lost a thread or lost a Goroutine in that process. So old code had these salient features. So if you see any of this and do see more opportunity, then more opportunity for concurrency, take that, right? That's what we learned. It had some mechanisms for syncing, but they were using WaitGroups, and we had to do a lot more bookkeeping to actually get out of those or terminate if we needed to terminate. Also, this was built or meant to serve a single target OS, and when we added another target OS, like we added Windows, things became super complicated as we started adding to the old code. So we found our guy. We found our guy to change. And in doing so, what did we fix? We fixed we tried to address via concurrency all these latencies. We figured out how important identifying those objects is, and finding single responsibility. So originally the code was a big long Go file calling out to a downloader, a compiler, and a publisher. And the new code actually is a bunch of directories which have at least 5 different files in them, because they are now broken down and their responsibilities are clear. We understand what is happening at each stage and what each object is supposed to do. And now the code is easy to understand because you can go from downloading to compiling to publish, and you know how the stages progress. So how do we measure success? We used to previously get 1 tile per day, and that used to take 6 to 8 hours. So if I came to work and did my email things and triggered the build because I have a new list of dependencies from a team, by the time I go home, I may or may not have a tile. And if I have a tile, then I could trigger the rest of the builds after initial verification or whatever, and then I might have a result in some time. Now we are getting 4 tiles a day because it takes 2 hours to do that. So that is 400% improvement than before. This allows us to actually use all the other tools we have to run parallel builds, because anyway by adding another OS, we also are starting to support more environments, and that is exponentially growing. So we cannot rely on one tile per day. And also these builds are now much more predictable. Anytime a tile fails, I know that is a genuine failure, and I can see the error. If I see that error, I can also find out which team who is sending us that dependency is responsible, and I can tell them that you need to fix this, or else we cannot ship, right? So that confusion was completely gone. And this is also ready to be now support multiple operating systems. If you come around and say, oh, now we have to support CentOS or Fedora or whatever else you need, this system is now ready. So that was a big win. We could actually running multiple builds a day. It was a huge thing for our developers. And also we moved away from the default behavior, just rerunning things without understanding what went wrong. So my learning from this was, don't be afraid. Don't be afraid to refactor. Don't be afraid to go back to the basics, meaning stick to your basics and try to bring that back into the new system you're working on. Don't be afraid to prioritize tech debt. There will always be forces that will tell you that this is not the right time, and quite often they're right, and there will be other business reasons. So we couldn't do this for the first 3, 4, 5 months because we were fighting other tech debt that was more important, because that was more important to deliver our tile, right? But once we got this opportunity, that is the time when you take it and then just run with it. And thanks to my colleagues, Kevin, Kelani, and Adrian, who actually trusted me and supported me along the way. I came in as a Go skeptic, and I was like, oh, GoLang cannot do that. And they actually, helped me learn and helped me, learn by doing. And that is the best way, I learn, at least. And that's all I had to share. And now I'm open for any questions.
Thank you so much, Sudhindra. I really appreciate it. Great talk. Anybody have any questions they'd like to ask this evening? Please feel free to unmute yourself and ask, or drop it in the chat, and I'll be happy to read it off for you. I think I want to see that movie at this point. I have not seen it yet. So I definitely will do that. And now I have a whole new perspective when I watch it as well. So definitely appreciate it. Sudhindra, what's the best way for people to contact you if they have any additional questions?
Oh, wait. So I am on Twitter.
Okay.
Let me stop. Wait. Is this the last?